As we have seen in compressible fluid flow through nozzles and orifices, we have derived what is maximum velocity, maximum mass flow rate and mass flow rate equations to calculate real life problems on compressible fluid flow through nozzles and orifices. So we have a problem over here which states that a tank contains air at the temperature of 30 degrees Celsius. So this means temperature T1 is given to us. The air flows through the tank into the atmosphere through a convergent nozzle. So from the tank it goes through a nozzle, through a convergent nozzle. Now this will be a distinguishing feature from other problems of compressible fluid flow, that it is flowing through the nozzle. If it was for a fluid which is flowing from a sonic flow to a supersonic flow, that will be related to normal shocks, so on and so forth. The diameter of the at the outlet of the nozzle is given to us as 25 centimeters. So this means D2 is given to us. Note that D2 is given to us. This means we can calculate the value of A2, that is area at the outlet. Assuming it is an adiabatic flow, find the mass flow rate. So mass flow rate will always contain A2. So this is what they have told us to find out. Through the air, when the nozzle pressure in the tank, when the of the air through the nozzle, when the pressure in the tank is given to us as 3.924 Newton per centimeter square and 33.35 Newton per centimeter square. Both pressures are given us as gauge pressure and both are in Newtons per centimeter square. This means we have to add atmospheric pressure to the gauge pressure. Here atmospheric pressure is given to us as well as the value of gamma as well as R is given to us. So all these values they have given to us. To calculate, the main feature over here is the mass flow rate. So let us write down the things which we know over here. First thing we know over here is the temperature which they have given. The temperature of air T1 is equals to 30 degrees Celsius, that is equals to 303 Kelvin. Second thing they have given to us as diameter D2, that is 25 millimeters. So this is 0.025 meters and A2 will be equals to pi by 4 into 0.025 the whole square. So this will be 0.000498 meter square. So we have calculated what is area of cross section. Then value of R they have mentioned, that is equals to 287 joule per kg Kelvin and gamma is equals to 1.4. Now Next thing which they have mentioned over here is the part which is mentioned, the tank contains air and the pressure of air in the tank which they have mentioned is equals to 3.924, that is gauge pressure. So P1 will be equals to P atmosphere plus P1 gauge pressure. So this will be equals to 10.104 plus P1 pressure, which is gauge pressure, is 3.924. Now both of them are in Newton per centimeter square. So we'll multiply into 10 raised to 4. We'll convert this into Newton per meter square. So this value comes out to be as P1 is equals to 14.028 into 10 to power 4 Newton per meter square. So we have calculated what is value of P1. Now as this exits from that entire tank, the outlet is exposed to the atmosphere. Since it is exposed to the atmosphere, the only pressure which is acting on the fluid which is traveling through the nozzle is the atmospheric pressure. Hence we can write over here P2 is equals to 10.104 into 10 to power 4 because P atmosphere is equals to P2 since it is exposed to the atmosphere. Now we have written all the data which is given to us, and except this data they have given to us as another data that is related to pressure P1, but that time it is exposed to another pressure that is 33.35. So we'll solve that case 2 later. We'll solve this case 1 now. Now, once we have seen all this data, we need to calculate mass flow rate. Now let us write down formula for mass flow rate. So the formula for mass flow rate is equals to A2 into square root of 2 gamma upon gamma minus 1 P1 rho 1 into a bracket. This is n raised to 2 upon gamma minus n raised to gamma minus 1 upon gamma. Gamma plus 1 upon gamma. So over here, what things we know, let us take those things. First, we know the value of gamma, which is 1.4. We know the value of P, that is equals to, we have calculated the value of P, which is equals to 14.08 into 10 to power 4. So we have the value of P1, which was equals to 14.028 into 10 to power 4. We know we can calculate value of N, which is N2 by which is P2 by P1, and now the only part which is remaining is rho 1. So let us calculate the two unknowns which we don't know over here, that is value of N and value of rho 1. So let us calculate the value of N. N is equals to P2 by P1. P2 is 10.104 into 10 to power 4. P1, which we have calculated, is 14.028 into 10 to power 4. The value of this ratio comes out to be as equals to 0.703. So this is a value of N. Now let us calculate the value of rho 1. We know that it is an adiabatic process. P1 upon rho 1 is equals to R into T1. We can calculate by applying this ideal gas equation. So rho 1 will be equals to P1 upon R into T1. So let us substitute the values. So this is equals to 14.028 into 10 to power 4 upon 287 into 303, that is the temperature. The density comes out to be as equals to 1.163 kg per meter cube. So we have evaluated the value of density rho 1. Now let us substitute in this equation and calculate the value of m dot. So over here our value of m dot, over here the value of m dot is equals to, let us write down the formula, A2 into square root of very big root 2 upon gamma minus 1 into P1 into rho 1 into n raised to 2 upon gamma minus n raised to gamma plus 1 upon gamma. So let us substitute the values one by one. So m dot is equals to 0.000494908 into square root of 2 into 1.4 upon 0.4, that is gamma minus 1, and P1 is equals to 14.03 into 10 to power 4 rho 1, which is equals to 1.613, and the value of N is equals to, we know the value as 0.703 raised to 2 upon 1.4 minus of 0.703 raised to gamma plus 1, gamma is 1.4 upon 1.4. So we have put down, substituted the value. Now on calculation of this entire part, we get this as m dot is equals to 0.146 kg per second. That is the mass flow rate which we have calculated. So in our problem, there was not only one initial pressure, there were two initial pressure. Initial pressure for the second part was equals to P1 is equals to P atmosphere plus P gauge of 1. So let us go to our problem and let us check this out. So the for first case it was equals to 3.924. Second case is 33.35. So this will be equals to, let us write down the values, that is P1 will be equals to P atmosphere 10.104 plus 33.35 into 10 to power 4. P1 is equals to 43.45 into 10 to power 4 Newton per meter square. This is value of P1. Now according to this, our value of N will change as well as value of rho will change. So N will be equals to P2 by P1. So this is equals to 10.104 into 10 to power 4 divided by 43.45 into 10 to power 4. So N comes out to be as 0.2375. That is value of N. And now we have to calculate the density. Again, we'll apply the same ideal gas equation. So let me write down this value as rho 1 will be equals to P1 upon R into T1. So this is 43.45 into 10 to power 4 upon 287. Temperature is 303 Kelvin. Then the density rho 1 comes out to be as equals to 4.995 kg per meter cube. If we substitute all these in the value of cross sectional area, in the value of mass flow rate, not cross sectional area, we'll get this as equals to m dot is equals to A2 into square root of 2 gamma upon gamma minus 1 into P1 rho 1 into n raised to 2 upon gamma minus n raised to gamma plus 1 upon gamma. We'll get the value as equals to m dot equals to 0.494 kg per second. So this will be the value of m dot. So we have understood how to apply this equation in calculating the values of mass flow rates. If the final pressure is not given to us, then we'll assume that it is exposed to atmosphere and we'll consider the atmospheric pressure. So I hope you have understood how to apply these equations of compressible fluid flow through nozzles and orifices in calculating the real life problems which we have accustomed over here, which we have seen over here. Thank you.